So before we take up a topic of low noise amplifier, we need to familiarize ourselves with the type of noises that occur in electronic components. So in this lecture, we will study two types of noise in two different type of devices, namely resistor and Mosfet. So noise, as it implies, means something unwanted. And here we are interested in unwanted current or voltages that might occur in devices or in circuit. So we are going to study electronic noise, and there are various type of electronic noise, and these types, they are categorized based on what is a physical phenomena inside device that leads to that unwanted current or voltage in the given device. So there are various types of electronic noises, but we will consider only two types in this lecture. However, when we start analyzing various circuits for the amplifier, we will see that we will consider only one type of noise, just to keep the thing simple. So as I pointed out, we will consider only two type of noise. First is called thermal noise, and second is flicker noise. This is also called 1/f noise, based on the location of the frequency or its dependence on the frequency. So each of these two noise we will study for two types of devices. First is going to be resistor, and second is going to be Mosfet. So first we will study thermal noise in a resistor. So as noise points out, it is something that is not desirable from a resistor, but it exists. And typically, when we talk about noise, noise is something which is unpredictable also. So there are two properties associated with noise. First is undesirable quantity, and second is random. So suppose we take a resistor R, and if we try to measure voltage across it and plot this voltage with time, then what we will see is a voltage varying very randomly like this, about 0. And this voltage will be across this resistor even if this resistor is not excited. That means there is no voltage applied across it. So as the name of this type of noise suggests, it arises because of the physical temperature of the resistor. And the value or this variation of the voltage will be typically of order of microvolt. We will take example and calculate it also. So now there are a few things that we should note about this noisy voltage across a resistor. First thing is that it is random. So random means we cannot write any mathematical expression for the this noisy voltage. So we cannot write no mathematical expression. Once we know the expression, you can always tell what will be the noise voltage at any given moment of time. And since we cannot predict what will be the voltage at any given time, so no expression can be written for it. So that means dealing with this noise in time domain is difficult. Second property, which you can guess by looking at the plot of this voltage with respect to time, is that the average value of this is 0. Average of this noisy voltage is equal to 0. But of course, we take this averaging over a large time duration. So this average value, this will be calculated as P and T dt from 0 to T, and then we take this T quite large. And this value will turn out to be 0. That means the net area enclosed by this plot is 0. Now the third property, which actually allows us to use or the deal with the noise produced by resistor in circuit, is that the average of square of this voltage is not 0. So we say that mean of square is not equal to 0. So how do we find out mean square? Similar to what we did for average. So first what we will have to do is we have to square it and then take the mean average. So this is the mean square value, and this is not equal to 0. Actually, this mean square voltage turns out to be equal to 4 K T R delta F. And of course, the unit is going to be volt square. So here, this K, small k, is Boltzmann constant. And T is absolute temperature. That means temperature of resistor R in Kelvin. And R is of course the resistor, and delta F is the bandwidth over which this mean square voltage is measured. So you can see that this is frequency dependent, bandwidth dependent noise source. So now this mean square voltage is bandwidth dependent. So one can find out what will be the mean square voltage over 1 Hertz. So So we are not going to use a separate symbol. From the expression, one can find out whether we are including the band or we are talking about per hertz quantity, mean square value. So this is one thing. Second is we can talk about the RMS value of the noise voltage. So square root of this mean square voltage. For this, we will adopt this symbol, and this is going to be square root of mean square, and this will be 4 kTr. And we can talk about this quantity for 1 hertz or with certain band, but let us say that we are talking for uh, 1 hertz band. So then this its unit will become volts per square hertz. Now let us try to get some idea what is the uh, amount of this noise voltage that will be produced for resistor. So we'll take an example just to get a feel of the numbers. Say for example, we want to know how much of noise, thermal noise will be produced by a 50 ohm resistor, because this is the most commonly encountered resistor in RF domain. And as we saw, this is temperature dependent, so we will have to pick one temperature. So let us say that we want to calculate at 25 degree Celsius, which amounts to 298 Kelvin. Right. And then we want to calculate this over a band of 100 kilohertz. So this is the register for which we want to do the calculation, and we know that Boltzmann constant is 1.38 into 10 raised to minus 23. So now first we will calculate the mean square value. So this value, if you calculate, this will be 4 into 1.38 into 10 raised minus 23 into 298 into 50 into 100 kilohertz, and this number will turn out to be 8.22 into 10 raised power minus 14. So this unit is going to be square. So this is the mean square value. Now we can ask what will be the RMS value. So RMS value is square root of this mean square value, and this one will be equal to 2.86 into 10 raised power minus 7. That means this is 0.287 microvolt. So this is going to be the RMS noise voltage for this resistor. So as was pointed out, it will be typically of order of this microvolt. And here you can see that we have taken bandwidth 100 kilohertz. So if you increase it, this noise is also going to increase. And of course, with the temperature also, this will increase. Now, what about the per hertz noise voltage? So if you calculate the mean square per hertz noise voltage, this will be 4 kTr, and this will turn out to be 8.22 into 10 raised power minus 19 volts per hertz. And for RMS, this will be square root of this number, previous number, 8.22 into 10 raised to minus 19. So this will turn out to be 9.066 into 10 raised to minus 10 volts per square root. Okay, so this was one example of noise voltage from a resistor. Now we will have to talk about thermal noise model of resistor, because whenever we have any electrical circuit which incorporates resistor, or for that matter any other device, and we want to analyze, then we need to substitute that device with a suitable electrical model so that we can use the electrical theories like KCL and KVL to analyze it. So now we are going to study the thermal noise model of resistor. So what does it mean? It means that we have a noisy resistor here, and we want to substitute it by a noiseless resistor of same value and maybe something else, so that the noise voltage that we see here across this resistor is same as the noise voltage that we see across these two terminals. So here this is noiseless. So question is, what shall we put here in this box? There are two models for a circuit, Norton model and Thevenin model. So similarly, we will see that there are actually two models for this resistor. Specifically, what we have shown here is going to be the Thevenin model. So first we will talk about Thevenin model. So in the Thevenin model, we know that we incorporate a voltage source. So Thevenin model says that we include a voltage source in series with noiseless resistor, and its RMS value, and we will designate this arbitrary symbol inside it to say that this is a noisy source, such that the RMS value is given by what we have already seen, 4 kT R delta F. In other words, its mean square value will be 4 kT R delta F. So now if you have this model, then you can see that the voltage that you will see across these two terminal will be what you will see across the actual noisy resistor. Now, what about the Norton model? So in the Norton model, we will have to incorporate a current source, and the current that will flow through the noiseless resistor this is noiseless, and here we have a current source, and I'm showing it by double-sided arrow again to mean that this is noisy. This should be equal to what we get noise from the previous model. right? So this is how we will calculate the IN. So now you can see that the IN flowing through R should produce this VN, right? So this implies IN is VN by R. And if you want to uh, go for the mean square, then it says that mean square IN is going to be mean square voltage divided by R square. So both of these two equations are valid and one can use them to find out the expression for corresponding IN. So let us use this one, 4 kT R delta by R square, and this is going to be mean square noise current. And this mean square noise current you can see is 4 kT G delta F, where G is conductance corresponding to the resistor. And now the RMS value is IN square root of 4 kT G delta F. So these are the two models. That means now if you have any circuit containing this resistor, and if you want to see that how much noise voltage you will observe at any other location in the circuit because of this particular resistor, then you substitute this resistor by one of these two models and then apply the circuit theory to do the analysis to find the voltage or current at desired location. So this is about a single resistor. Now let us see that what happens when we have two resistors in series. So we want to get a feel that what will happen to the total noise voltage. So we have a resistor R1 connected in series with R2. And we are interested in knowing this final voltage. And we also want to see if we can have any equivalent resistor such that we get the same voltage across this equivalent resistor. Because for the purpose of resistors, we know that these two resistors, they can be simply added and we can substitute a new resistor of that value in the circuit and everything will remain same. So similarly for noise also, can we do something like that? So here what will happen is this will produce a noise voltage Vn1 and this one will produce a noise voltage Vn2, and both are going to be random. So this is Vn2, this is Vn1 in time domain, right? So there will be another voltage here, V equivalent, and this will also is going to be random. So we saw that we have been tackling the noise produced by resistor RMS value or using the mean square value. So we want to see that which of the two voltages can be added for these two series resistors. So when we have this Vn1 here, Vn2 here, and if you want to measure the total is of course going to be sum of these two, obviously. So in time domain, we will definitely see the sum of these two voltages. But let us see that what happens in mean square domain and root mean square domain. So now from here, we will try to find out the mean square and ultimately the RMS value. So now the mean square value, so this is total voltage and the mean square voltage Vn is going to be limit T very large and average of square of the total. Now this total can be substituted in terms of the individual voltages. That is Vn1 plus Vn2 in time domain, of course. So we can expand this. Vn1 square plus Vn2 square plus 2 into Vn1 V2 dt. So this amounts to finding out the mean value of these three quantities. So we are already familiar with the mean square values of the first two. So mean square of this will simply become Vn1 mean square. Mean square of this will become Vn2 mean square. But now we have this quantity mean square of product of the two voltages. So now we have to find out what is going to be this mean square voltage. So see that we have these two noise voltages here, noise 1, noise 2. Both are random, right? So if you multiply them, these two, the resultant function is also going to be random, right? So what we will see for Vn1 into Vn2 is again a random function. And what we are doing here is basically we are taking average of this new random function. So we can say Vn12. And this average is definitely going to be 0. So what we will be left with is the sum of means two individual voltages. And we say that we got this thing, this quantity equal to 0 by conveying that Vn1 and Vn2 are uncorrelated. So meaning of this uncorrelated means that if I know Vn1 completely, I will never be able to predict what will be Vn2 in any way. If there is a correlation, then knowing one of the quantities will allow you to know at least partially the other quantity. Right? So this situation is similar to what we encounter in vector. That means if we have a vector and if we split it into its x component, ax and ay, and if I tell you about ax, you will never be able to say what is ay, because both are completely orthogonal or uncorrelated. So uncorrelated, orthogonality, they basically mean same thing, that one does not have any relation with the other one. The two are totally independent. And knowing one will not allow you to predict or know anything about the other. So ay can be anything if I specify ax. Similarly, if ay is known, ax could be anything. Only when I tell what is a and what is ax, then one can say what is ay. So this is in short the meaning of uncorrelation between these two noise sources. So here what we did was we took two resistors R1 and R2 of two different values. But this uncorrelation between these two resistors remain valid even if these two are of same value. Not only that, even if they are fabricated in exactly same way, using exactly same material, in the exactly same scenario, even then the noise voltages, because of these two resistors, they are going to be totally different. That means uncorrelated. So now from this equation, we can see that the total mean square for the series of two resistors is simply going to be sum of the resistors as if the two resistors are added, and then we find out the mean square voltage. So this leads to that if we have a series combination of two resistors, you simply find out the equivalent resistor to find out the its mean square noise voltage. And this will be valid for parallel combination as well. But now let us see that what will happen to the RMS value. Can they also be added? So the RMS value is going to be square root of the mean square value that we have found out. So here we can write it 4kt R1 plus R2 delta F. Now we can see that this is not equal to 4kt R1 delta F plus 4kt R2 delta F. So this is not equal to the individual voltages. So we have seen that only the mean square voltages add, not the root mean square. The root mean square voltages of two series resistors, they do not add. So we can add only either in time domain or in the mean square domain. So this was for the very simple network of two resistors. Now what will happen if we have a more general resistor network? Say for example, so we have a big resistive network and these two ports are available, these two terminals to us. Then what will be the mean square voltage that we will see across these two terminals? So here the previous analysis can be extended, and what one can do is first find out Thevenin resistance. And once you have find out the Thevenin resistance, the mean square noise voltage from this resistive network is simply going to be 4kt RTH delta F. So this is the more general result stated without proof, and previous case will be one specific example of this. Now one can ask, what if we have a complex network? So that means we have now resistors, capacitors also inside this network. That means R, C, and possibly L also. So this will have Thevenin impedance ZTH, and we again want to see that what will be the mean square noise voltage across these two terminals. So here also, fortunately, the previous result can be extended, and we can say that this will be 4kt. But now the only the resistive part of this network. So this analysis can be, or result can be extended to more complex network also. Now we are going to talk about the power spectral density of resistive noise source. So we have a resistor whose thermal noise is known. So for that case, we want to know what will be the power spectral density. So here power spectral density, as we know, is basically the density of power with respect to spectral component. That means spectrum, that means frequency. So what we want to know is a quantity like watts per hertz. So let us try to find out this power spectral density. So we already know the mean square voltage from a resistor given by 4 kTr delta F, and this is volt square. And so now what we do, we divide it to get a quantity which is volt square per. So we have divided both sides by resistor, and this unit volts per ohm, we know that is watt. So this is related with the power of resistor R, noise power. Now what we wanted to know here is watts per hertz quantity, and that is going to be the power spectral density. So this amount of power is carried by the noise produced by resistor R over band delta F. So now power per hertz can be obtained by dividing this quantity by the bandwidth, and this will become 4 kT. So here now what we have is watt per hertz. So here we see that the power spectral density of a resistor is frequency and bandwidth independent. Depends only upon the temperature. Now we will talk about the noise for the second device which we are going to encounter in circuits, namely the low noise amplifier, that is Mosfet. So we are now going to talk about thermal noise of a Mosfet. So there are actually more than one noise sources associated with a MOS, but we are going to keep the thing simple, and we will talk about the noise produced by the channel. So what we are going to talk about is only the noise produced by the channel of a MOSFET. So here also question arises that if we have a noisy MOSFET, so this is noisy, that means this current is going to show some random fluctuation. So how do we model this? So a noisy MOSFET can be modeled by a noiseless MOSFET, noiseless, in parallel with a noise source. In parallel with a noise current source, of course, such that the noise current that you see between drain and source here for noisy case is also going to be exactly same as the noise current that you see between this model. It's a drain and source. So this is, you can say, the Norton model. That means we are substituting a current source to account for the noise current between drain and source. And here, this mean square noise current between drain and source is given by 4 kT gamma GD0. So expression you can see is similar to what we already encountered for the resistor. There is a great deal of similarity between these two. Here, K and T, they are as usual, the Boltzmann constant and the physical temperature in Kelvin of the Mosfet. And GD0 is transconductance of the MOS for drain to source voltage is equal to 0. And this gamma is unitless constant which depends upon the channel size and the biasing also. That means gate to source voltage, sorry, drain to source voltage. So this gamma will be determined by the channel dimension and drain to source voltages. So here this gamma is equal to 1 for VDS is equal to 0. However, if the MOS is in saturation, that means when drain to source voltage is not equal to 0, then this turns out to be 2 by 3 for long channel MOSFET. And this becomes 2 for short channel. So some of the authors, what they do is they avoid all this distinction and distinction between transconductance, and they take a simple expression for KT gamma GM instead of taking GD0 for the mean square noise current due to MOS. Right. So this was the Norton model. Now what about the Thevenin model? That means if you want to include a voltage source, then here it should be included. So keep in mind that the current that we see between drain and source is a consequence of voltage at the gate of the MOS. In fact, to be more specific, between gate and source. That means now we can substitute another model for noisy source in terms of voltage if we include a voltage source at the gate. So we can say that the this will be Thevenin model, and in this case noisy MOS is modeled by a voltage source at the gate So now in this case also, we will get the same current that we got earlier for the previous model between drain and source. And we know that converted into this current, drain current, by a factor of Gm, the transconductance. So this can be said that this Vn multiplied by Gm is going to give rise to the noise current, or in other words, Gm square into mean square voltage is equal to mean square current. So here Gm square for Vn mean square is equal to In by Gm square. So this will be 4k T gamma GD0 by Gm square. And in the simpler case, when we take GD0 as Gm, then this becomes 4kT gamma 1 by Gm. So here in all these expressions, we have omitted delta F. So delta F can be included if you want to be more complete. Delta F is present in all these expressions as well. So this is for, or rather when we make this assumption. So this was the story of the thermal noise for these two components, that means resistor and MOS. Now what about the flicker noise component for these two resistors and MOSFETs? So second type of noise is flicker noise, and this is called 1 by F noise because it increases as the frequency reduces. So first about resistor. So this noise for resistor is also called excess noise, because when noise is measured across a resistor, we found that we have more noise that we obtain from the expression of the thermal noise. So this additional noise is attributed to this type of noise. So this is one thing related with this noise for resistor. Second is, this exists only when resistor is excited by DC current. DC current is flowing through R. And this noise, the flicker noise of resistor, increases if this DC current through R goes up. So when this DC current increases, the flicker noise also increases. And this flicker noise that we see across a resistor is dependent not only upon the material which is used to fabricate the resistor, but also on the technique. So this is material and technique dependent for fabrication of resistor. And it is found that for carbon film resistors, they have very less flicker noise. And for this type of resistor, that means for the carbon film resistor, the mean square voltage can be written as a constant K divided by F, and this F is the frequency, and it is this thing which leads to its name 1 by R and nature also. So here K is constant, not the Boltzmann constant, but it will be material dependent. Material dependent. F is frequency. A is area of R, and R square is sheet resistivity, and V is voltage across R. Recall that this depends upon the current flowing through this, and the current will be decided by voltage across R. And delta F is bandwidth. So this is the expression as was pointed out, that the noise produced by resistors depends upon material technique. So it will vary from resistor to resistor of same value. But if it is carbon sheet, then this is going to be the expression. Now, what about the flicker noise in MOS? So here, as was the case with the thermal noise, the Mosfet can be modeled in terms of voltage source or in terms of the current source. So voltage source model of MOS for its flicker noise. So this is, and we want to talk about only the flicker noise. So this will be equivalent to voltage at the gate and expression for this flicker noise mean square is given by K divided by F as usual, previous case, but now K is going to be different, not the same as that of the resistor case. So they are different. 1 by WLCOX square. So here K is constant, and this is going to be process dependent. That means how the MOS is fabricated. F is frequency, and W is channel width, L is channel length, COX is channel capacitance per unit area, so here you can see that when we reduce the frequency, the noise voltage increases, and the same thing was observed for the resistor also. F is in the denominator, and that is why this noise is called 1 by F noise. One can obtain this, it's a current in terms of by doing this formulation. That Gm square Vn mean square should be equal to noise current mean square. So using this, we can find out the expression for flicker mean square current, and this will turn out to be simply Gm square K by F 1 by W square. Now what happens here is that if you see the power spectrum of the noise for say Mosfet, then as this uh, expression says that this will dominate at low frequency. So as the frequency goes up, this will increase. So this is the flicker noise. Now we know that MOSFET will also produce thermal noise. And for the thermal noise, we have seen that its power spectral density is constant. So the thermal noise produced will be something like this. So there will be a point where the flicker noise and the thermal noise both become equal. And that is called the corner frequency for this device. So at FC, which is corner frequency, what happens is flicker noise becomes equal to thermal noise. So we can equate the drain thermal noise current to the drain flicker noise current for a MOSFET. So for a MOS, what we will have is INF mean square is equal to IN mean square. So this we have already found out. This was Gm square K by F 1 by WLCOX, and this was equal to 4KT gamma, and here we can have GD0. Keep in mind that we are talking this thing with respect to per Hertz quantity. So from here we can find out this corner frequency FC, and this FC will be equal to, sorry, this is UX square, will be equal to Gm square K. So these two K's on left and right hand side, they are different. This denominator is Boltzmann constant K, and numerator is for device depending upon the process. So this is the mean square per Hertz. So these are the two different types of noises for two different most commonly encountered devices. And when we analyze the amplifier for its noise behavior, namely in the low noise amplifier, we will consider only the thermal noise, just to keep the thing simpler.